Welcome to today's video. Today we're going to extend our notion of integrability from just boxes to arbitrary domains. So you remember that so far we have only defined volume integrals over boxes. And of course, an important question here is how can we extend that to arbitrary or at least more general sets? And that's what we want to do in this video. So far, remember, we have only defined integrals over boxes. What about more general domains? And we'll start with a simple definition that, at least in theory, extends our notion of integration to pretty much any kind of set that we want if the integrals actually exist. Of course, the more pressing question here is how do we actually compute these integrals, and that's what we're going to talk about in the next step then. Okay, but let's first see how we can extend our notion of integration from boxes to arbitrary sets. So we let D be an arbitrary domain. So D is a set in R to the n. We have a function f defined on D, mapping to the reals. And let's say we also have a box. So B is a box in R to the n that contains the set D. So D needs to be bounded, otherwise things will get difficult, and we just assume there's a box that bounds this set. So B, a box with D contained in B. And that especially implies D is bounded. But that's pretty much the only restriction that we will impose. We will then define a new function f d that is defined on the box B and maps to the reals. And we'll simply define fd of x as f of x if x is contained in the set D, or 0 if x is in the set B but not in D. So the idea is to extend the function f to the whole box B by simply keeping the function values as they were over the set D, over the domain D, and setting them to 0 everywhere else on the box. And then we say the function f is Riemann integrable over D if this extension fd is Riemann integrable over the box. And we know how to integrate over boxes. Okay, so that's the definition here. Then f is Riemann integrable over D if fd is Riemann integrable over B, and we define the integral over D to be that of fd over B. Okay, so we set the integral of f of x dx over D to be equal to the integral of fd of x dx over the box B. So basically the setting is like this. We have this set D that can look really arbitrary here, like this. So this is D, we want to integrate over D. And what we do is we start with a box that contains the set D, like this here. So that's our box B. And we just define a new function over B by setting it to 0 outside of the green domain D. Okay, so that's the very simple but very successful idea. Using this definition, we can then also define a volume or a measure for the set D itself, or for arbitrary sets D. We can define a volume for sets by just integrating a constant function of 1 over those sets. And that's what we call a measure or a volume of a set. So furthermore, a set D in R to the n is called, and we call that Jordan-measurable. If the constant function x maps to 1 is integrable over D. And in that case, we denote the n-dimensional volume of D by vol of D, and that is defined as the integral over D of the function 1 dx. Okay, so this way we can associate a volume to every set that is Jordan measurable. And as the definition suggests, there may be sets that are actually not Jordan measurable, that don't have a well-defined measure. And that's where this integration doesn't work. Problem is this does not generally work for arbitrary sets. And we wouldn't expect it to. Because there are sets that look so strange that you wouldn't expect them to have a meaningful integral. Let's have a look at an example here. So let's say we take the set D as follows. We'll define that as all x's in the box 0, 1 squared. So far it's all good. And now we just take those x's, those x vectors, where both coordinates are in Q. So x is in Q squared. Yeah, that means we want just the rational points. So this is obviously contained in the box 0, 1 squared. And we want just the rational points in this box. Okay, what we want is we want to integrate the one function, so we want to compute the volume of D. Now, does that set have a meaningful volume? Two things you might suggest here. First one is, as we know, the rational points are dense in that box. So that means for every point in the box, in every neighborhood of that point, small as it may be, there is a rational point. So basically the rational points cover all of that box, right? So you may suggest that the volume is actually the same as that of the original box. One possible suggestion. You could also argue that, well, there's lots and lots of points in that box that are not contained in D. So wouldn't it be right if the volume of D would be 0? Because there's a lot more non-rational points than rational points. Or maybe the real answer is somewhere in between. Maybe the volume is something strange like 1 over e to the pi. Who knows? Well, let's find out. Let's see what our theory actually says about that. I already mentioned every box of positive diameter that is contained in that set D contains a rational point, because the rationals are dense in the reals. So every box of positive diameter contains a rational point, because the rationals are dense in the reals. Meaning for every real number there is a rational arbitrarily close to that number. So what does that mean for integration? Well, if we have a box of possibly very small diameter, then there's always a rational point contained in that box. And that means the one function on that box, the maximum of the function on that box will always be 1. Right? It's 0 on all the non-rational points because those are not in D. It's 1 on all the points that are in D. So for every box of positive diameter, there's always a point that is contained in D in that box. So the maximum of the function f, of the one function on that box, is always 1. The minimum is always 0, on the other hand. Okay? And that's the second point that we should mention. Every box also contains an irrational point. So let's sum that up again. What we want to do is we want to integrate the function 1 over D. So for every box, we'll have a look at the function 1D, that is defined as being 1 on the points in D and 0 on the points not in D. Okay? So consider a function 1D defined on our box 0, 1 squared, where 1D of x is 1 for x in D and 0 for x not in D. Okay. Then for every box of positive diameter in D, the maximum of that function 1D over the box is always 1. There always is a rational point in that box. And the minimum is always 0, because there is always a non-rational point in that box as well. Well, what does that mean? For the upper Riemann sums, we'll always get 1. For the lower Riemann sum, we'll always get 0. So upper Riemann sum is 1. Lower Riemann sum is 0. No matter how small we make the boxes, that doesn't change. So as a consequence, those two do not converge to the same value. And that means, simply as it is, the function 1 is not Riemann integrable over D. So, in other words, D is not Jordan measurable. So it doesn't have a meaningful value, at least not in the framework that we have defined here. Of course, one could think about other possible measures, extensions of that theory that we did. And actually there's a huge field on that. It's called measure theory. It's basically the basis of modern probability theory. And maybe you'll have a look at that in your statistics course at some point. But we're not going to dig deeper into that topic. That would be a topic for a whole own lecture. What we will do instead is we'll consider sets that have a somewhat nice description so that we can actually tackle the integration of those sets in a computational way. And we're going to do that in one of our next videos. I'll see you then.